Weiss.
Okay, so my talk is, I guess this was supposed to be the optical flow session, because all of us who are here worked on optical flow, but I will actually talk about things I did not work on during my thesis, but that I discussed with TED. And I think this is something that maybe all of us former students of TED can relate to, is that in addition to the research supervision, TED would come up to us with all these questions and ideas that stay in your mind for a long time. And I'll talk about two such discussions that I now know the answer to. So here's the first one. This is 1995, almost 30 years ago. TED comes up to me and says, well, what happens if you represent images by a series of convolutions, nonlinearities, convolutions, nonlinearities? So I say, well, without nonlinearities, this is just like a single convolution. And then TED says, I can actually hear his voice now, I know. But what about with nonlinearities? And I said, well, I need to get back to my ellipses. So I was working on these ellipses. Second conversation. This is right after Heger and Bergen published this really nice paper on generating textures. So TED comes up to me and he says, well, Heger and Bergen are generating textures by matching histograms. Wouldn't it be better to match moments? And I say, well, how would you decide which moments to match? TED says, I don't know. But I don't like discrete histograms. In general, TED doesn't like discrete things. He likes everything that needs to be continuous. Well, so I answered, I need to get back to my ellipses. Okay. So this talk is based on, so it took me, 20-something years. And we now know that representing images by repeated convolutions and nonlinearities is a great idea. Matching moments is also a great idea. And then this paper that we published last year in CVPR says that actually this is both of these ideas are almost the same idea. Okay, so this idea of using repeated convolutions and nonlinearities now goes, as a representation for images, now goes under the name perceptual losses. So now it's become very standard that if we want to compare these two images, what we do is we pass them through some pre-trained neural network like VGG, and we look at the activations in these intermediate layers. And now when we want to say how similar these two images are, we don't measure it in the pixel domain, we measure it through these intermediate representations. So this is exactly TED's idea, because we represent images. The image representation is the output of a series of convolutions, nonlinearities, convolutions, and nonlinearities. And one way to know that this was a good idea is it has more than 4,900 citations. And it actually does work much better than representing images based on pixel values. So for example, if you train a network to do some task and you use these so-called perceptual losses, you get much better results than if you use an L2 or an L1 loss. And that's been replicated by many people, including us. And it also does a very good job of matching what humans will judge as similar. So this is work that Philip, who's probably here somewhere, was involved in, is that you take an image and you distort it in two possible ways, and you ask a human which of these is more similar to the original image. And if you look at something like the L2 loss, it will say that this is more similar to the original image, that these two are more similar than these two are. And yet humans will invariably say that these two are more similar. And this also happens to be the case for these perceptual losses. So there's a very good numerical match between the similarities in this two alternative force choice that humans will do and these perceptual losses. So this is just to show that this idea that TED had, which I sort of ignored, of representing images by repeated convolutions and nonlinearities is a great idea. Okay. Second great idea is this idea of using moments. And this is some very nice work by Arthur Gretton and Bernard Schulkopf, who basically answered this problem that I had with moments, that you don't know which moments to use. So this is a picture from their paper. If you take these two distributions, the red points and the blue points, If you look at their first moment, their means, they'll be different. If you look at the second moment, their variances, they're actually the same. So how do you know which moment you should be using? And they introduced something called the MMD, the maximum mean discrepancy, which basically says, look over an infinite space of possible moments, and the distance between the distributions is how different these two moments, the worst case moment will be between the two distributions P and Q. So if f here is a linear function, this is the mean. If it's x squared, you get the second moment. In general, you can search this infinite family of functions and choose the worst case, and that's called the maximum mean discrepancy. And the amazing thing about this paper is they showed that even though there's an infinite family of moments here that is being calculated, you can do it in closed form and do it very efficiently, even if x is high dimensional. So for example, you can do it for things like patches. So you can take an image and divide it into a lot of small patches and ask how similar is the image distribution, is the patch distribution, sorry, between these two images. And patches are high dimensional. And again, going back to my discussion with Ted, that means there are many possible moments that one could use. And yet, remarkably, there is this closed form solution that allows us to efficiently say how different the worst case moment will within this infinite family of moments. And it's given by this particular closed form formula. So again, going back to our discussion, this idea of matching moments and avoiding histograms is also a great idea. But what I want to talk about today, which was our contribution, is the fact that these two ideas are the same. And in fact, Ted already knew that. And this goes back to the Bergen and Adelson paper on texture perception, where they pointed out that if you take something like linear filters followed by a nonlinearity and then another linear operation, that gives you an energy measure, which is sort of a moment. So this connection between moments on the one hand and these repeated convolutions, nonlinearities, was already present in this work. But what we asked is what happens when you have many filters and many layers, and we generalize this result. So again, our result shows that these two ideas are almost the same. So let me just explain what almost means. So if you look at this neural net over here, we call it a simplified CNN. If you take the two images, you apply the first layer of convolution, which has some spatial extent, in this case 3 by 3, and you have convolutions, nonlinearities, convolutions, nonlinearities for many layers. But all these layers are what are known as one-by-one convolutions. They don't extend the receptive field. They just jumble up the different channels. And then in the end, you have this average pooling over some window. So this is not VGG. It's a different type of architecture, but this is one that we could analyze. And for this, we can show mathematically that as the width of this network, as the number of filters goes to infinity, comparing images based on this final pooling layer is exactly the same as calculating the MMD between the distribution of patches in the two images. So these two ideas, in one case, representing images with nonlinearities and convolutions, and the other idea is looking at patch histograms, small patch distributions, end up being actually the same. And our theorems were about these very idealized CNNs, not like VGG, but in fact, what we said, okay, let's forget about the theorems and just use this very simple idea of MMD instead of perceptual loss. So we're going to compare images directly by doing this MMD loss, which we understand, instead of this VGG loss, which has all sorts of deep learning in it, and we don't really understand it. And how well does it work? So in our experiments, it works just as well as if we were to use the VGG loss. So this is an example for super resolution. If you train it, you probably can't see well on the projector, but if you train a super resolution network with the L2 loss, you get these blurred images out. If you train it with the VGG loss, this idea of using repeated convolutions, nonlinearities, you get things that are much sharper and look better. This is, again, a previous result, not our own. But if you use the MMD loss, which is much simpler, we understand what it's doing, it actually works better than the VGG loss, and it's also very sharp and gives you high-quality results. And in fact, it matches human perceptual judgments just as well as the VGG loss. So again, if you look at this image and you ask a neural net, the perceptual loss, is it more similar to this or to that, then the neural network prefers this one, as do humans, but we don't really understand why the neural network prefers it. And this is also true for the MMD loss, which again just divides these two images into patches and measures the distance between the distribution of patches. And then we understand why it's more similar, because these have sort of similar patches, and these have very different patches. So we've had a lot of success with replacing these perceptual losses with MMD losses, but there's some problems with MMD loss. Mainly, I can go more into it if you're interested. It's very sensitive to how you define this infinite family of possible moments, which so there's hyperparameters associated with that, and you have to tweak them for every different task. So we've gone on to use another histogram-free method called SWD, which I don't have time to go into, but if you ask me, I can go into it more. But it's another way of taking two images, splitting it up into a bunch of patches, and measuring the distance and distribution between the two patches without ever constructing a histogram. And when you do this, you can do all sorts of tasks very, very efficiently. You can change the style of an image. You can do generate multiple images from a single training image. And you can do, just like Hugo and Bergen, but 30 years later, you can also do texture synthesis. And it's all based on this idea of estimating the distance between distributions of patches in the two images in a way that avoids building histograms. Okay, so let me summarize. Representing images by repeated convolutions and nonlinearities is a great idea. Matching moments and avoiding histograms is also a great idea. They are actually almost the same idea. And I think what we're finding now in 2022 is that matching patch distributions without building histograms is a powerful paradigm for image comparison and manipulation. Thank you. Questions? You're supposed to moderate.
Thank you for the prompt. Any questions?
Any questions?
Ruth?
How big does the set of possible moments have to be? And is there any way to
So the set of moments is infinite, which is sort of weird. So it's it's infinite, so it's very big. And the amazing thing is that even though it's infinite, there's this math that allows you to do it in finite time and do it, solve it efficiently. So you don't really have to choose the moments because you're optimizing over this infinite set. That's sort of the thing I said in the end, the way you define the infinite set will sort of change what you end up doing, and that's the part I don't like about MMD, and that's why I went to this SWD, which avoids it.
Any other questions? Okay, thank you here again.
This work? Does it? Okay.
Okay, our next speaker is Jitendra